So in the last slide, we talked about making bonding orbitals by overlapping nicely the atomic orbitals on two atoms. So we could overlap two s orbitals and make a sigma bonding orbital. It was a lower energy than the individual atomic orbitals. We could overlap two pz orbitals that were pointing at each other to make a sigma bonding orbital. And then we could overlap, first of all, two px orbitals to make a pi bonding orbital, and two py orbitals to make a pi bonding orbital. And we said very, very simplistically, a single bond was a sigma bond, a double bond was a sigma bond and a pi bond, and a triple bond was a sigma bond and two pi bonds. Now we're going to take the next step into molecular orbital theory. And one of the ideas that I want to bring up now, and we'll keep going, and we'll probably encounter it again later on when we start talking about fun coordination complexes, is that there is a theoretical observation that I term conservation of orbitals. And what that does is it says that if you combine two atomic orbitals together, you need to have two new molecular orbitals. And of course, what we've seen thus far is we've only seen one. We said two s orbitals make one sigma bonding orbital in which you can put two electrons. Two px orbitals coming together make one pi bonding orbital into which you can put two electrons. Where's that missing orbital? Where's the extra orbital that we should have made? Well, in this movie, I'm just going to introduce the idea of the anti-bonding orbital, and then we'll see if we can't apply our new molecular orbital theory to some very simple types of molecules, homonuclear diatomics. So anyway, let's think about a sigma bond. As you've already seen, we take two atoms that have got one s orbitals, bring them together, and we have that nice little overlap. And what we said was that that gives us a sigma bonding orbital. And this is exactly what I drew on the last slide. And of course, in that sigma bonding orbital, because it's a bonding orbital, an electron in there can see both nuclei. Here it is here, you can see that nucleus, you can see that nucleus. And of course it's sigma because it includes the line between the nuclei. Now if I look at this combination orbital here that I got by just bringing together those two 1s's and overlap, we've taken care of that little shaded bit there, that blue shaded bit, and that's a manual shading. I apologize for the way it looks. Okay, but there's all this volume here outside that I'm going to shade in light blue that we haven't taken into account. That was a volume in the atomic orbitals, but now that's a volume that we have not worried about. Well, it needs to be there. And let's sort of draw it on out there pretty like this. This is essentially the volume on the left-hand side of the left-hand nucleus, the right-hand side of the right-hand nucleus. It's the volume that was there in the 1s orbitals, but it's nothing to do with the overlap part of it. Now this volume here, if there's an electron in this volume, well then not only is it only seen one nucleus, but that nucleus is really close to the other nucleus. So as far as the electron is concerned, nothing changed. As far as the nuclei are concerned, everything changed. They're really close to another nucleus. So we call this volume here an anti-bonding orbital. And we give it a little star there to indicate that it's an anti-bonding orbital. And in an anti-bonding orbital, if there's an electron in that, it can only see the one nucleus. So you'd say it's just like it was in the original atom, but in the original atom, this nucleus is miles from the other nucleus. In this bond, the nucleus is really close to the other nucleus. So that's a bad energy situation. So now, if we put together our 1s and our 1s that we had before, not only are we getting a lower energy bonding orbital, the volume between the nuclei, but we've got a higher energy anti-bonding orbital. We've essentially, at this very simplistic way of thinking about it, taken the space, the volume that was defined originally by those two atomic orbitals, we pulled out the bit that's common to both, the overlap, and we've said that's your bonding orbital, just like we did in the last movie. But when we've taken this extraneous volume here that's not used for the overlap, and we said, well, that would be a higher energy anti-bonding orbital. By the way, both the bonding and the anti-bonding orbital are sigma, because even the anti-bonding orbital contains that line that goes between the nuclei. Now, this was a very, very, very oversimplified introduction to the anti-bonding orbital. So on the next slide, I'm going to bring in something a lot nastier, something that will immediately turn some of you off, but don't worry about it. I just need you to get the vague idea of what we're talking about. So if you understood the way that I described getting the bonding and the anti-bonding off the last slide, then that will probably help you understand the rest of these movies. But we need to just introduce a little bit more of a deeper thought in order to fully explain it. And that's going to require that we remember that orbitals and electrons, but in this case orbitals, are actually as much waves as anything else. So that's a wave. And let's say that that is describing one of our atomic orbitals, which I'm just going to call phi 1. And there's another wave that I'm going to say describes the atomic orbital on the second atom, phi 2. Now, what we're doing when we're bringing these orbitals together is we're going to combine those wave functions. We're going to combine those waves. Now, we could combine the waves in a nice happy fashion where we add them together, and where there's the overlap of the adding together, it adds to it, and so we get a much nicer, bigger wave. Okay, and that's just like what we're talking about with the bonding orbital. Here's atomic orbital number 1, atomic orbital number 2. They overlap there, and because they are in phase, in other words, the peak of 2 and the peak of 1 match up, then they add to each other. They augment each other, and we get that nice bonding orbital, that nice happy volume there. On the other hand, what would happen if these waves, this one and this one, were out of phase? In other words, the bottom of psi 1 and the top of psi 2 matched up like this. Well, then what's going to happen is that they'll cancel each other out, won't they? And you get a little picture like this. And the way that we would describe that mathematically is we'd say, instead of adding these waves together, we subtracted this one from that one. And when we subtract the second one from the first one, and we get the cancelling out in that area of overlap, still got some wave here, and we still got some wave here. And that's what I'm drawing as my nice, pretty little anti-bonding orbital. I'm also bringing into account, by the way, the idea of the positive signs of the waves. Here, this wave on the left-hand side is positive, so I'll always draw positives as a empty orbital, not shaded, and over here is the negatives, so here I've got my negative shaded orbital. So the bonding, positive overlap between the waves, adding the wave functions together, if you like. The anti-bonding, negative cancelling out overlap between the waves in that overlap area, but we've still got some of the waves on either side giving us the anti-bonding area. Two atomic orbitals together give us bonding and anti-bonding new volumes.